In May 1981, at MIT, Richard Feynman stood before a small crowd. He came to say one line: nature isn't classical, and if you want to make a simulation of nature, you'd better make it quantum mechanical. 13 years later, mathematics built for that machine would have data thieves stealing files they cannot read. Here is what I am going to show you: how a machine that barely exists already broke the internet's locks on paper, and why your data is being harvested today to be read tomorrow.
Go back to the wall Feynman was pointing at. Classical computers, the kind you are watching this on, store everything as zeros and ones, a switch either on or off. But the universe underneath is not a switch. At the subatomic level, particles exist in overlapping clouds of probability, and to track every quantum state exactly, the memory a classical computer needs explodes exponentially. Add more particles, and that number doubles every single time. At around 120 of them, the hard drive holding the state would have to weigh more than the planet Mars. The Russian mathematician Yuri Manin and the American physicist Paul Benioff had pointed at this limit a year earlier, in 1980. Feynman turned it into a challenge. Don't fight the physics, use it. Build a machine that computes with quantum mechanics instead of against it. For years, it stayed an idea with no proof. Then, in 1985, the physicist David Deutsch supplied one. He described a universal quantum Turing machine on paper and proved it could do things no classical machine can match. He built nothing, but he handed the world a blueprint, and buried in its mathematics was a weapon nobody had noticed yet. As quantum computing hit the mainstream, its physics got butchered by oversimplification. The most pervasive myth is that a quantum computer is fast because it tries every possible answer at once. People picture a classical computer walking down every dead end of a maze one by one, while the quantum computer clones itself, runs every path at once, and instantly finds the exit. This is entirely false. If you put a 1,000-qubit machine into a giant superposition holding every possible answer, and then measure it, it does not hand you the right one. The state collapses and spits out a single, random, useless result. It does not know what you were looking for. A quantum computer does not blindly check all paths. It uses interference. Think of noise-canceling headphones. They don't block sound by building a wall. They listen to the incoming wave and generate an exact opposite wave so that when the two meet, they cancel and leave silence. A quantum algorithm works the same way. The programmer designs it so that the probability waves of all the wrong answers destructively interfere. They crash together and cancel, while the wave of the correct answer constructively interferes and amplifies itself. When the scientist finally measures, they get the right answer, not because the machine checked every option, but because the wrong ones were engineered to erase themselves first. Remember that trick: waves canceling waves. It is not just how the machine computes, it is exactly how the weapon works. A second myth refuses to die: entanglement. Entangle two particles, and measuring one instantly fixes the state of the other, no matter how far apart they are. Because that happens instantly, people keep claiming quantum computers will let us talk faster than light. The mechanics forbid it. When you measure your entangled qubit, the result, a 0 or a 1, is completely random. You cannot choose it. To send me the word hello, you would need a deliberate sequence of ones and zeros, but all you can do is flip a random coin. Because the outcome is random, no information rides on that instant collapse. To even confirm the two were correlated, you still have to phone or email me over an ordinary network, and that is capped by the speed of light. Entanglement is real. A faster-than-light telephone, it is not. But the real threat to your data never needed speed. It needed patience and one algorithm. In 1994, at Bell Labs in New Jersey, a mathematician named Peter Shor found that algorithm. He took the exact trick from the headphones: interference, wrong answers canceling, the right one amplifying, and aimed it at one question:
What is the hidden period, the repeating rhythm of a mathematical function? On a classical computer, finding that period for a large number takes effectively forever. Shor showed a quantum machine could tune the interference so the correct period is the one left standing. That stays abstract until you learn what hides behind the period. The encryption protecting the internet, the TLS handshake that puts the little lock in your browser, relies on asymmetric keys, a public lock everyone can see, and a private key that is supposed to be impossible to work out from it. For the RSA keys, working out that private key means finding exactly this hidden period. Shor's algorithm finds it. A close cousin of the same algorithm cracks the elliptical curve keys guarding most connections today. So here is the part that matters. The key does not crack your password. It cracks the lock your password travels inside, which raises the only question that counts. How far away is that key? The honest answer is measured in qubits. IBM's newest processor, Nighthawk, runs 120, the same number that just cost us a planet-sized hard drive. IBM has built chips with over 1,000 qubits. Nighthawk's 120 are the ones wired well enough to run real circuits. The best current estimate for turning Shor's algorithm against the encryption guarding your bank is under 1 million physical qubits running error correction, down from 20 million a few years ago under standard assumptions about error rates. The gap is enormous. It is also closing. These qubits are absurdly fragile. A stray photon or a flicker of heat collapses the state and corrupts the calculation. IBM's answer is to scale up standard superconducting qubits and fix the errors with error-correcting codes. Microsoft made a stranger bet. Picture a secret written on a sheet of paper. Spill coffee on it and it is gone. That is a normal qubit, ruined by noise. But tear the paper in half, keep one piece in New York and send the other to Tokyo, and coffee in New York cannot destroy the secret because it lives in neither half alone. That is what a topological qubit attempts, splitting the information across the two ends of a nanowire so local noise can't reach it. Microsoft is trying to build this with its Majorana 1 chip, though whether its devices have really demonstrated the topological protection they need is still disputed. And every few months, some company announces quantum advantage, only for several of those claims to be narrowed later by unexpectedly fast classical algorithms. The key is coming, it's just not here yet. Which is exactly why the theft has already started. Security agencies have a name for it. Harvest now, decrypt later. Adversaries are recording encrypted traffic today, files they cannot open. Betting the machine to open it is only years away. The NSA and its partner agencies name this threat in the open and warn that adversaries may be doing it now. Anything that must stay secret for the next decade is already living on borrowed time. Nowhere is this sharper than on a blockchain. A public ledger is permanent by design, so every old transaction sits in the open forever in any wallet whose public key is already visible on the chain. The earliest coins or any address that's been reused is a lock with no expiry date. Wait for the machine, derive the private key, empty it. That is why the world is quietly migrating to post-quantum cryptography. In 2024, the standards body, NIST, finalized new algorithms like ML-Chem built to survive Shor. And the same machine that can break the locks guarding our data is also learning to build things. In 2026, IBM, RIKEN, and the Cleveland Clinic paired quantum processors with two of the world's fastest supercomputers to model a protein of 12,500 atoms, the largest known to be simulated with quantum hardware. The lockpick and the medicine are the same device. In 1981, Feynman asked for a machine that could simulate nature. He never saw it built. He is going to get it anyway. And the same machine will break the public key locks the internet was built on. The blueprint is real, the qubits are scaling, and the data is already being harvested. So here is the question. Would you re-encrypt everything today, or bet the machine is 20 years away? Tell me in the comments and subscribe to LynxSifts Tech and Science. I'll see you in the next one.